Hello everyone, and welcome to our Hot Topics session. I would like to welcome everyone here. I'm your chair, Tessa Bent, and I would also like to give a special welcome to our remote participants. So this is part of a new initiative where we are going to be streaming and recording some of the sessions at the ASA meetings for people who can't be here physically. So I just want to thank our speakers, who are some of our test participants in this program, and for their willingness to participate and have their talks online. So without further ado, we will start our first exciting talk, which is going to be presented by Aubrey Espana on hot topics in underwater acoustics.
Okay, can everybody hear me okay? All right, so let me start by acknowledging my collaborators on this project, Kevin Williams and Steve Kargl, and we're from the Applied Physics Laboratory at the University of Washington, and also our sponsors for this program are ONR and CERTA. So let me start off with some motivation. Unexploded ordnance, or UXOs, are basically unexploded weapons that did not detonate when originally deployed. I show some examples in the right side of the page here. These can be howitzer shells, TPT rounds, artillery shells. And so the problem is that following World War II, there was a number of munitions, they had a lot of munitions left over. So a viable solution at the time was to go out and dump these into the ocean. These are now causing problems for the environment. Maybe the contents are leaking out, or they're starting to migrate up into areas on shore. Maybe because of water sports now, people are scuba diving in areas where they used to not be able to. And so now we're having problems with public safety, right? So there's a viable, popular solution for this is broadband sonar. Why use sound? Sound can travel long distances in the water. Visibility is not a problem, so you can find these things in murky, dark waters. It can penetrate the seafloor. So for example, this bottom right corner here, where you have something that's completely buried, you're still going to be able to find this with sound. And also it can penetrate the objects itself. So you have the potential to be able to distinguish things about the material composition or the internal structures of it. So the difficulty is that the acoustic response of UXOs are highly dependent on a number of different factors. Operational choices, how high your vehicle flies off the sea floor, what path it takes around the objects, environmental factors, is it fully buried, partially buried, is there a ripple pattern on the sea floor, is it a windy day so you have a high sea state, and then also the processing tools. How do you choose to extract the most relevant information? How do you train and test your automatic algorithms? All that stuff is going to make this very difficult. So it's this interdisciplinary nature of the problem that's going to be challenging. Now, to our knowledge, the approach thus far has been very categorized. Namely, you're going to, and rightly so, you're going to have experts in their respective fields, and they're going to be focusing on trying to advance technologies within their own field. All right? So maybe the target scattering people have been able to make advancements in how they understand the target physics, and they try to pass that off to the automatic target recognition people and say, you should use this physics. Maybe the environmental people, maybe they've identified that something that they thought about one environment is now different in a different environment. Hey, ATR guys, you better watch out for this. But simply passing off this information, you can actually lose a lot, right? There's a lot of physics that can get lost along the way. And so we need to rethink this flow chart, right? We need to ask ourselves, what is it ultimately we're trying to do? So of course, we're trying to develop these automatic algorithms that can go out and say, yes, I think this is a UXO, or no, it's not a UXO. But what good are these algorithms if we can't say how well we think they're going to perform? All right, so ultimately, let's try to rethink this in terms of more a performance-oriented chain. All right, so now we're going to go out and take some raw data, and we're going to find ways to represent that data in terms of a data product that's going to highlight the important physics. So now instead of separating the target and the environment, let's think about the target in the environment response, or the tier response. Then let's try to bring that into the ATR world and see if that helps us improve things. So what I'm going to do for the remainder of this talk is I'm going to attempt to walk through each of these boxes. All right, I want to stress that each of these boxes, in and of itself, you could do a multi-day tutorial course on each of these subjects. I'm going to barely scratch the surface, try to show you a little example of what goes on behind the scenes. And along the way, I'm going to try to answer some of these questions. Number one, what is a UXO? What does it look like acoustically? Where are we in our ability to understand and predict its acoustic response? Then how is it that we go about trying to find them? So this performance-driven chain of trying to say yes or no, I think this is a UXO. And finally, once we have these automatic algorithms, how good are we? How good are they? How good do we think they are? And can we, even with dragging a little bit of physics along with us, can we start to optimize that process? Okay, so I'm going to go very quickly through this, the raw data. I want to get right to the data products. This is just, if you're going to look at a UXO, it really depends how you're going to view it and what frequency of sound you're going to use. Here's an example of what you would see in the raw time domain data. This is just if you did a linear pass two objects, you get time on the x-axis, cross range on the y-axis, versus if you did a circular path around it, you'd get this full angular spectrum as a function of time. Let's get right into our data products. I focus on low frequency, but I want to start off showing you high frequency data because it's more intuitive. All right, so if we do a linear pass and we're pinging these targets with our sonar, you're going to get something, you're going to get a bright scattering off of the object and see something bright that looks like roughly the size of the object, and it's going to cast a big shadow behind it. All right, now if you do a circle around this, you actually no longer will have a shadow. You're going to light up the shape of the object. You're going to see what it looks like, its size and shape. Now when you go to low frequency, it's much less intuitive. So I'm going to spend the next couple of slides really talking about these low frequency data products, which are acoustic color plots. So what this is you take your data and you convert it to a frequency and angle space, all right? And so they're plots of the absolute target strength as a function of frequency on the x-axis and aspect angle on the y-axis. I've shown you the case for a full circular path, and I've marked little important locations here. These little crosses right here mark when you're looking broadside to a target. That corresponds to these bright responses right here. And then end on, maybe you have a flat end cap, so you get a bright response, or maybe you have a pointed nose and that manifests as a null in the pattern, all right? Why do we want to use low frequency? Why bother to use it if when you stare at it, this doesn't really look like a UXO? The reason is that the wavelength of sound is on the order of the target dimensions. And so the sound can actually couple into vibrational modes of the object and can reveal things about the material differences. In this example here, you see a real artillery shell versus two copies of it, or solid aluminum, solid steel, and you can see how different these acoustic color templates look with just material differences. So our group's bread and butter is really understanding and predicting the response of these things. So we understand how they behave in the free field, how sound couples to it and makes these things vibrate. Now what happens when you go and stick this thing down in contact with the C4, things get very complicated, all right? The example of the changes that you see in the acoustic color are given here, where you have a solid aluminum UXO that's been placed down, and you're going to drive a circular path around it at 10-meter range. Then you're going to drive around it at 5-meter. Then you're going to bury the thing and see what it looks like at that 5-meter range. And you can see, number one, that the response becomes much brighter compared to its free field response on the left side here. And number two, these resonances move around. They're now excited at different angles. We understand this because the presence of the sediment has now created these multiple pathways for sound. So sound can actually bounce on and off the sediment before it hits the target or on the way back. So the way that these pathways add together is what creates the changes that you see in this acoustic color template. Where are we in being able to predict the acoustic response? So one of the methods that our group uses is a hybrid finite element propagation modeling method. I've listed some references here. People in the back of the room probably can't read those, so you can come and find me afterwards and I'll give you some references. The basics is that we use a propagation model to handle the propagation of sound to and from the target, and then the actual target interaction, the sound, how the sound interacts with the target is handled with a finite element model. Here's this is to show you where we're at, how well we can do with this type of hybrid model. This is that same data I showed 2 slides back for that solid aluminum UXO at 10-meter range. 5-meter range and then buried at 5 meters. And here's the hybrid model results. So you can see that we do a good job of being able to predict and capture the dominant acoustic phenomenon that you see in these data products. So now that we have these models, how can we use them? So we like to use these to dissect the physics. That way we can understand the physics and try to bring that along with us the rest of the process. One example that's going to become important at the very end of this talk is the shape versus elastic response. And so if you take your finite element model and compute the rigid equivalent of this, and you look at what is that shape information, how is the shape dictating what our acoustic color looks like, you see that it tends to dominate the broad side and the end-on responses, right? So that'll become important later on. Okay, so hopefully now you have a little bit of a picture of what these things look like acoustically. So let's dive in and see how we go about trying to find them. All right. Now I want to stress I'm only going to show you, this is one simple example of how you could do this. It's a kernel-based classification method. All right. The reason we're doing probably the most rudimentary thing is because I am a physicist and I'm going to attempt to jump in and understand what the ATR people are doing in the most basic sense. And I'm going to see if we can drag some physics along with us and try to improve something by doing that. So the idea is that you're going to start off, you need to have a database of data products, all right? And so this database needs to contain both target and non-target items, right? Now, ultimately, we're going to want to we're going to want to learn this automatic algorithm, but then we're going to need to go out and test and see how well do I think this is going to perform before I jump into the field and try to use it. So let's take our database, divide it into 2 sets. First set is our training set. Step 1 of this process is to go through the feature extraction process. Feature, what is a feature? So I can say that it's derived from a measurable descriptive target characteristic. Now, although we focus on low frequency, I want to show the high frequency because, again, you can picture it in your head. You can really visually understand what's going on. So ideally, a feature is going to provide a clear separation between a target and a non-target. It's not going to be sensitive to pose or range, and it's going to be stable under environmental conditions. So for a high-frequency image, it could be geometric characteristics, such as the mean highlight or the mean shadow. The difficulty is that you need to be able to extract these things automatically. That's where you run into problems, where you might have things that your automatic feature extraction process is, say, keying off of and saying that's part of the target shadow, but it's not actually. That's where we're going to run into problems. All right, now let's go through low frequency. What would these things look like from a low frequency data product, acoustic color data product? So essentially what you're doing is you're doing a template matching or a pattern recognition process. So you need to come up with some sort of measure of how similar is this acoustic template to the other acoustic template. It's going to be related to the maximum of the cross correlation, but it's not exactly that. So let me just go through a little pictorial example with, remember we have our training set. So let's take each of our little training sets, which just had 4 little acoustic color things, and let's compare it to itself and then every single other one in our training set. Ideally, it's going to look exactly like itself and it's not going to look like anything else. That would be the ideal case. But in reality, you would get something that looks like this, where the first one looks a little bit like the second one, nothing like the fourth one. And what would happen if it turned out the fourth one was actually the same target as number 1, just at a different range? I mean, that's the complexity of this problem, right? So you can play games by applying a nonlinear kernel, which will try to increase the separation between your targets and your non-targets. But the only takeaway I want you to take here is that positive off-diagonal things cause problems for us. The last step is training the classifier. So in this example, this is just a relevance vector machine or an RVM. So what this RVM does is it's going to go out and it's going to pick out what it thinks are the most relevant feature vectors. Feature vectors being these vectors of numbers here. So I've taken these acoustic color templates and reduced them down to 1 number, which is a measure of the similarity. All right? And when I say relevant, I mean the most discriminatory, the features that are the most discriminatory between target and non-target. Okay, so we've done this. We're armed with this automatic algorithm now. Let's go through, how do we actually measure how well we think it's going to do? All right? And so this is where you're going to test it out. And the way that we we measure how well we think it's going to perform is through a receiver operating characteristic curve, or a ROC curve. Okay, these give you a measure of how often you correctly classify a target versus how often you're wrong. So our y-axis is going to be our true positive rate. So it's going to be every time that I correctly said a target was a target. Our y-axis is our false positive rate. Every time I incorrectly identified a non-target as a target. There's two extremes I want to point out here. Along the diagonal is this dashed line. That means that you did no better than a coin toss. It's just a 50-50. This dark dashed line right here is the best case scenario. It's the one that starts at 0 and goes straight up to 100. Straight up to 100 and over. So that's going to be the best you can possibly do. Okay, so how would we optimize our performance? All right, so in order to do this, I need to take you through just really quickly a real life example. So over the past couple of years, we've done a number of experiments out in the Gulf of Mexico and St. Andrews Bay in Panama City, Florida, in conjunction with the Naval Surface Warfare Center. So at our disposal right now, we have 90 acoustic color templates. So let's take these acoustic color templates and let's section them off, 18 sections, each one of them. We're going to uniformly overlap these sections. So our training set is going to be 1620 by 1620. Let's go through the feature extraction process, apply our nonlinear kernel, and here's what it looks like. The point here is that you have a lot of these positive off-diagonal components which are going to cause us problems. These things over here. So we run our RVM and it chooses 10% of these that it says are the most relevant vectors. So there's 162 relevant vectors. Okay, now we need to test this thing. So the way I'm going to create this test set is I'm going to take the same 90 acoustic color templates, I'm going to add some white noise, and I'm going to section them randomly. Okay. I'm going to go off and test this new automatic algorithm that I have. And there's our ROC curve. Not that stellar, not too bad. But here's where it gets fun. If you go in and look at the relevant vectors and you ask yourself where in the acoustic color template are these coming from, it turns out a good majority of them are coming from broadside and end-on responses. If you remember, about 10 minutes ago, I told you that the broadside and end-on is dominated by just the rigid shape of the object. And so it's no surprise that things that are roughly the same size are going to look the same. The classifier is going to think that those are targets, and maybe they're not. So is there a way that we could pull off this shape and elastic separation and improve our performance? So it turns out, in a very approximate sense, most of the shape information is contained in the early time part of the signal, and most of the elastic stuff is in the late time part of the signal. And so if you just do a simple separation in time, and you send just your shape-only stuff, so your early time, through this whole performance process, then you send just the elastic or the late time information through that process, and you come up with your ROC curve, you end up with this. And so the important thing here is that red curve was that original one I showed you. The green curve is the elastic-only information, and we've actually been able to improve the performance. And again, this was just dragging in some physics very naively through this ATR process, a very rudimentary ATR process. So in conclusion, I hope that you can at least understand or have an appreciation for how difficult this problem is because of the interdisciplinary nature of it. I walked you through each of these boxes very basically, and we went through a little pictorial performance estimation example, but then tried to quickly breeze through a real example and showed you that by armed with just a little bit of physics, we can actually make some big improvements in this. Thank you. So, I can't hear you, I'm sorry.
How about that? I presume what you're looking at is Ordnance.
Yes, yeah.
Is it unexploded Ordnance?
Yes.
So we want to move it?
Yes. Mm-hmm.
Now, if you define low frequency,
Yeah. So our low frequency, I say 1 to 30 kilohertz. And that's just because that's what we use during our experiments. It's the wavelengths on the order of these UXO target shapes. Mhm. Yes.
How much of the stuff is rusted out?
Yeah, that's a good question. Yeah, a lot of it.
All, and you're not going to let the costs go down to get it. Hopefully shell it up, not dangerous. And that's, you know.
So it depends on really what problem you're trying to solve. If you're trying to go in operationally and get through a region quickly, that's a different problem than if you're on kind of the DoD side of trying to clean up sites. And on that site, they have to remediate everything with 100% certainty. That's what they've been mandated to do. So that problem, they have to find it all. And it's very costly to go in and dig these things up, so they really don't want false alarms. They really want you to be, yeah. Yeah.
That's all the time we have. Thank you, Aubrey.